Hey everybody, so on this one, it says we've got a designer's working on a new roller coaster and she begins by making a scale model. On this model, a car of total mass 0.5 kilograms moves with negligible friction along the track shown in the figure above. The car is given an initial speed, v0 equals 1.5 meters per second at the top of the first hill of height 2 meters. Point A is located at a height of 1.9 meters at the top of the second hill. Calculate the speed of the car at point A, and we'll call that VA. So let's find VA there. So the first thing you need to realize is that this is conservation of energy. If something moves and it goes from one height to another. So always think about what energies you have in the beginning and what energies you have in the end. So in the beginning, we've got some gravitational potential energy, and we've got some kinetic energy. And then as we roll down over here we'll also have some gravitational potential energy and also some kinetic energy there. Now a little trick that you can do, it's not necessary, but it makes things a little bit easier, is to call this point the ground right here. What that does is if you say A is the ground, then when you're on the ground, you have no gravitational potential energy. And that will make that a little bit simpler. But there's a small little trade-off here. If that is the ground, and the ground is 1.9 meters high, then this hill is not 2 meters high, this hill is 0.1 meters high, and that is going to be important going forward. So now, second step, plug in the equations for each of these. So this should be mass times gravity times the change in height here, plus 1/2 times mass times the initial velocity there, and that's got to be equal to 1/2 times mass times the final velocity squared there. Now, you can see here that there is a mass in every term, and the mass will cancel out as they do in all conservation of energy problems that don't involve springs or work being done. So now we can start to plug these in here. Gravity is 10, the height is 0.1. Here we have 1/2, the initial velocity is 1.5 squared, and 1/2, and that's equal to the final velocity squared. So just do some of your algebra there, and you should get that the velocity here is about 2.06 meters per second. Moving on to the second part. It says, on the figure below, draw and label vectors to represent the forces, so it's a free body diagram, on the car at point A. So point A is when it's on top of that hill there. It may even help to sort of draw. Imagine that it's, you don't actually want to do this on your free body diagram, but it's sitting on that hill. And that may make you realize that we've got the force of gravity down, and we've got a normal force back up. Now, how did I know? They didn't say you had to do this to draw the force of gravity bigger than the normal force. It's because this car is going in a circle. In what way is the center of the circle? That way. So anything going in a circle must have a net force pointing towards the center of the circle. And so that's how we know the force of gravity has got to be bigger than the normal force. Next part there, they say, calculate the magnitude of the force on the track, aka the normal force, at point A. So right here. So this is a centripetal problem here. So you want to start all centripetal problems the same. The sum of the forces is equal to mass times the centripetal acceleration there. Next part is, what are the forces? We've got force of gravity positive because it's in, minus normal because it points away, is equal to m v squared over r. So solving for normal force, I'm going to move this over to the other side and subtract this term over there. So normal equals Fg minus mv squared over r. And now I can finally start to plug in for these. So normal then will equal Fg will be the mass, which is 0.5 times gravity, which is 10, minus this part here. So minus the mass again, which is 0.5. Velocity on top of that hill, remember, was 2.06 squared. And the diameter, or the radius of that circle was 0.95. And if you work all of that out, you should get a normal force equal to about 4.55 newtons. So And that makes sense. It's got to be less. As it goes over top of one of these hills, it wants to sort of fly off. So if it was just sitting there, its normal force would be equal to its weight, which would be 5. So next part here, it says the track is modified at point A. The track is modified, and at point A, friction is introduced in order to stop the car. Calculate the work that must be done by friction in order to accomplish this. So we want to stop this thing. We want to change its kinetic energy, and the work will be equal to that change in kinetic energy. So since it's going to lose all of its kinetic energy, that change is just going to be equal to a negative of its initial kinetic energy. So we can just plug that in there. That's going to be 1/2 mv0 squared. By the way, that's v0 here. So it's 2.06 meters per second. So this is a new initial velocity. This is the new beginning. So don't use the 1.5 there. And now we just plug in for there. So that'll be negative 0.5 times the initial velocity of 2.06. Square that, and you should get from there 1.06 joules is our initial kinetic energy here. That also means that's our loss of kinetic energy. That also is our work done, and I got to include that negative there because we lost that energy. All right, final page here. If the car is stopped by point B, find the average force that must be exerted by friction. So remember, not only is the change in kinetic energy what we found equal to the work, but work is also equal to force times distance times the cosine of the angle of the two there. So now let's start to plug in here. We already know this. We just found it. It's negative 1.06 joules. We're looking for that force there of friction. The distance they gave to us, if you look on this sheet, the distance it moved here was 1.5 meters. So let's plug that in, 1.5 meters, and cosine of 180 degrees, because it's going to be moving this way, but the friction force is going to be back that way. That's just going to get us a negative there. So the force then, if you work all of this out, should be about 0.7 newtons there. Final question is, explain how your answers for part A would change if the mass was increased to 1 kilogram. Let's go all the way back to part A here. Well, if we changed it from 0.5 kilograms to 1 kilogram, look at this. The mass is canceled out, so it won't matter. So how would your answers change? They wouldn't, because masses cancel. Whoops, I forgot to write what cancels. Mass cancels. There we go.